So, we will start the course with optical waveguide theory. Optical waveguides are the basic elements for integrated optics. So, light propagation optical waveguides is important to understand their properties, their design and so on. So, there are many types of optical waveguides like slab waveguides, ridge waveguides, channel waveguides. Of course, there are also optical fibers. We need to interface optical fibers with integrated optical devices. So, we need to understand their properties. So, the mathematics of this is quite simple, and we will start with the basic of optical wave theory and proceed to understand these properties. So, a typical integrated optical waveguide looks like this. You have a substrate of some material like glass, and using lithography, which we will see later on, we can create regions where the refractive index is high like this. This is a typical optical waveguide called channel waveguide. The cross section of this looks like this. There is a higher refractive index region here in the guiding region and lower refractive index in the substrate and in the cover regions. So, this is called the substrate. This is the guiding region. And of course, the cover or air. So, this is called a channel waveguide. Typically, this can be formed on a glass substrate by ion exchange into it. As you know, the typical glass consists of sodium ions. You can exchange sodium ions with silver ions to create higher refractive index. Suppose you create the whole surface of a substrate. Suppose you take a glass slide and make whole of the top surface as the waveguide, then this is called the slab waveguide. Substrate, guide and cover. This is called a slab waveguide. So, here the whole top surface is the waveguide. So, how do we characterize these waveguides is an important question. What are the factors, what are the structural parameters which will define an optical waveguide and its design. So, the most important property of course is the dimensions, like width, then the depth and so on, and also optically the most important parameter is called the refractive index profile. As you have observed, the refractive index varies with the dimensions, and we can represent it using n, x, y, where x and y are the coordinate axes. As an example, for a slab waveguide, we can say, suppose if it is can be drawn like this, and you can say the refractive index is n1 in the guiding region, n2 in the substrate and n3 in the cover, and we can draw the refractive index profile as follows. If this is the x axis, this is the n is a function of x, and it has got a refractive index of N1 in the guiding region and N2 in the substrate region and N3 outside, the refractive index profile looks something like this. So, refractive index profile is variation of the refractive index with dimensions. In the case of a channel waveguide, we can represent the refractive index n in terms of 2 coordinate variables. So, this is a transverse cross section what I have shown. Now, before going into the properties of optical waveguides, we need to understand what are called the modes of optical waveguides. In microwaves and other branches of physics, you must have come across modes of the waveguides or propagation. So, mode of an optical waveguide can be defined as a pattern of electric and magnetic fields. We know the light is electromagnetic wave and has got electric and magnetic fields which are governed by Maxwell's equations. So, the propagation of light in optical waveguides is also governed by Maxwell's equations. We need not go into the Maxwell's equations right now, but we know that a wave equation can be derived from the Maxwell's equations. So, the typical form of a wave equation looks like this. So, where psi is the wave function representing any of the fields, electric or magnetic field components, and v is the speed of the light in the waveguide. So, this is called the time dependent form, and del square is the operator which contains transverse components x, y, z or in any other coordinate system that we choose. So, we can say that a wave equation is a result of Maxwell's equations which can be used to study the propagation of optical waveguides. So, there are several parameters with us like x, y, z, and the structural parameters go in the form of the velocity which can be expressed in terms of the medium properties by the electrical permeability and magnetic permeability and electric permittivity of the medium properties. So, a mode of an optical waveguide can be defined as a pattern of electric and magnetic fields which can be obtained from the wave equation, and we talk about the wave propagation in terms of harmonic fields. If psi is the wave function dependent on x, y, z and t, we can study the properties of the waveguides in terms of a harmonic field defined as having a single frequency. So, we can call them as monochromatic waves of a certain given frequency omega t. So, this is equivalent to saying that we are going to study the Fourier components of the field. So, if we express psi as psi x comma y comma z, say let me put a bar above this to say that this is only a coefficient e power omega t, we can reduce the wave equation to del square psi equals omega square by v square. I am differentiating this twice and then substituting, and psi bar. We can also express the velocity in terms of frequency into the wavelength, and reduce this equation further to, let me put velocity is c by n, where n is the refractive index of the medium, and the wavelength multiplied by the frequency will give the velocity divided by n, and after a little bit of manipulation we can reduce this to psi square plus k 0 square n square psi equal to 0. So, the refractive index profile is appearing in the wave equation as follows. This is called the Helmholtz equation, which does not contain the time variation. This is for the harmonic fields. So, we are talking about the waveguides which have a cross section. I will draw once again the waveguide geometry. So, you have a refractive index which is a function of x comma y only, and along the propagation direction the refractive index is not varying. So, let us say that the propagation is in the z direction, and we can define a mode which varies as e power I omega t e power I beta z in the z direction. So, I can replace once again this psi in terms of, okay, let me put x comma y comma z as going psi, I will use another symbol psi tilde x comma y into e power I beta z. So, we can define a mode as a component which varies as e power I omega t plus or minus beta z. So, with this we can reduce the wave equation as follows. So, I am using the same notation, ignoring the tilde and bar placed above psi. So, the psi represents the mode field, and along with beta characterizes the mode. So, the mode has got a field pattern and the propagation constant, and I have shown the 2-dimensional form x square and y square. For a channel waveguide you have both the components, and if we are talking about a 2-dimensional waveguide like a slab waveguide, we can ignore one of the variations like y. Then for a 2D waveguide we can reduce this to d square psi by dx square plus k 0 square n square minus beta square multiplied by psi equal to 0. Just to remind that n is the structural parameter which varies with the x or y. So, the problem is to solve for the wave function as well as the propagation constant simultaneously. So, let us take an example and try to solve this for a typical example. Before that, as we know, the electromagnetic fields inside the optical waveguide has many components, x component, y component, z component and so on, and electric fields Ex, Ey, Ez and Hx, Hy, Hz. In principle all the components can exist and can be important, but it is possible to reduce the study of optical waveguides to a single component. Sometimes if you are not interested in the polarization issues etc., the basic properties of optical waveguides can be studied using what can be called as a scalar theory. Where only one component is important and all the other components could be derived from the given component. We will go into the details later on, but let us start with the scalar approach and see the properties of the waveguides and relate them to the vector properties where polarization and other properties will be important. For this, let us consider the slab waveguide that we have discussed earlier. For slab waveguide, so the slab waveguide, the geometry is like this, where you have a refractive index n1 in the guiding region, n2 in the substrate region and n3 in the cover region, and I will put the axis x, and I will take a specific case of a symmetric slab waveguide. A slab waveguide can be called symmetric when the superstate also has a refractive index n2. And what is expected of this? Before we derive, let us look at what is expected of this as a solution. So, the wave equation, or first of all let me write the refractive index profile. I will draw it in the same axis that we have chosen to represent the waveguide, and let me take the origin as the middle, and the refractive index profile could be drawn like this, n of x, and this x direction. This is the, let me say the width of the waveguide is w, width or depth, and from minus w by 2 to plus w by 2 you have the refractive index n1, and outside is the refractive index n2. This is a geometry and this is a refractive index profile, and the corresponding wave equation turns out to be d square psi by d x square plus k 0 square n square minus beta square of psi equal to 0. Our problem is to find the psi and beta simultaneously. We should remember that n1, this contains refractive index profile n1, where which has got a refractive index n1 in the core and n2 in the cladding. We can also separate out these, we can write these equations differently for core as well as cladding, and then later on match. We can say d psi 1 by dx square in the core region, the field, and k 0 square where refractive index is n1 and beta and psi 1 equal to 0, and in the cladding region d square psi 2 by dx square plus k 0 square n 2 square minus beta square of psi 2 equal to 0. So, we have written the, we have split the wave equation into the core region and cladding region, but we should remind that the psi is a composite function having some value in the core and another value in the cladding, and refractive index also having a different values in the core and cladding, but the beta, the propagation constant, belongs to the entire waveguide and wave propagation. So, we can, the form of the equation is familiar. Suppose we replace the constant. Now, n1 and n2 are constants appearing as k and alpha. Let me define as k square and alpha square, where k square can be defined as k 0 square n1 square minus beta square. Okay, I do not need to put again this. And also alpha square being defined in terms of the constant lying there. I will define it as a negative parameter. I will explain why it is negative, k 0 square n 2 square minus beta square, negative sign. So, if the equation inside the core is d square x square by d square psi by dx square k 0 square and or plus k square psi equal to 0. Then we know this is the equation for a simple harmonic motion, and we know the solutions in terms of the trigonometric functions. Psi of x as a sin kx plus b cos kx. So, this represents a field which is oscillating along the x direction. We can write similarly the typical solution for the cladding region, and we see that instead of k there is an alpha, and if alpha is a positive then we can expect an oscillating solution inside the core and cladding also. And if we choose alpha to be negative, or if we choose beta such that k 0 and 2 square is less than beta square, then alpha is negative, and we can represent a field in the cladding in terms of the exponential fields, exponentially rising and exponentially decaying fields. So, this is a typical form of the mode field profile, and we can express d is suppose d square psi by dx square, this is psi 2 in the cladding region minus alpha square into psi 2 equal to 0. Now, with alpha with a negative, alpha being defined in terms of beta square minus k 0 square and 2 square. So, now we know the solutions of this equation in terms of the exponential functions. Psi 2 is c into exponential of alpha x plus d into exponential of minus alpha x. So, we have these solutions to the wave equation as oscillating fields inside the core region and exponentially rising or decaying fields in the cladding region. We can take a physical explanation saying that the fields of an optical waveguide, the desirable form of the fields of an optical waveguide as oscillating fields which gradually decay to infinity, and choosing the constants will be an important problem now. So, if you look at the waveguide and the equations, we can say that the field should be continuous at the boundary. So, now we will use the boundary conditions to choose the parameters or the arbitrary constants appearing in the equations. So, we have a field which is trigonometric inside the core region and exponentially decaying or reducing in the cladding region. We can give a rigorous mathematical explanation or meaning for the shape of the fields that we choose, but for understanding purposes let us now choose a very tentative approach and say that the fields are required to go to 0 at infinity and have an oscillating form given by the trigonometric functions in this region. So, and also the boundary conditions imply that the fields should be continuous at the boundaries. So, let us force that the field psi 1 equal to psi 2 at x equals w by 2 and on the other point and the other side also. Similarly, we have many constants in the arbitrary constants in the solutions. So, we need more boundary conditions to evaluate the further constants. Let us force one more boundary condition saying that the derivatives of the fields are continuous at x equal to w by 2 and the fields go to infinity, fields go to 0 at x equals infinity. So, with these conditions we can evaluate the fields, and remind once again that we need to solve for the beta and the mode field. Now, in the case of a symmetric slab waveguide, we can expect two types of modes. From the symmetry of the geometry, we can expect that the field for x greater than 0 and x less than 0 are symmetric or antisymmetric. So, the field can be symmetric like this or antisymmetric like this, and only if it is enough if we solve the equations for x greater than 0. So, by looking at the solutions that we have, psi equals a sin kx plus b cos kx. For the case of mode 1, we can say that this is like a cosine field, and for the sake of for the second mode, you can say that the field is like sine. To quicken the process, let us take a symmetric mode where cos is the mode field inside the core region, and say that the by choosing constant a equal to 0, we can force it to be symmetric. This can be done more rigorously, more mathematically. So, let us choose psi to be b cos kx in the core region. Similarly, if we look at the field in the cladding region, where we have psi equals c into e power alpha x and d into e power minus alpha x, we have chosen that the field to be going to 0 at infinity. So, if we take alpha as a positive quantity, so this field should decay in the cladding if we choose only this part of the field. In other words, we can put c equal to 0 for this and choose the field to be d into e power minus alpha x in the cladding region. So, we have the psi of x is b cos kx for x less than w by 2 and d e power minus alpha x for x greater than w by 2. Now, let us apply the boundary conditions to find out the exact form of the field, and once again to remind you that we need to find out the beta which is there embedded inside the k and alpha in some complicated way. So, at x equals w by 2, psi 1 equals psi 2 implies b cos kappa x, or x I will replace by w by 2, equals d e power minus alpha into w by 2. And once again at x equal to w by 2, if I force psi 1 dash equal to psi 2 dash, we get, let us differentiate first and then apply the boundary condition. So, psi dash x is kappa into b into sine kappa x and minus alpha into d into e power minus alpha x. So, we have the, by matching the boundaries, we have minus kappa into b into sine kappa into w by 2 equals minus alpha into d into e power minus alpha x. So, this is equation 1 and this is equation 2 to solve for the arbitrary constants b, d and so on. So, from the first equation I can say I can find out one constant d to be equal to e power alpha into w by 2 into cos kappa into w by 2. We can use up the first equation to find out, to eliminate one arbitrary constant d. We can use the second equation along with the first equation to eliminate the other arbitrary constant b, but one of our choice, one of our intentions is to find the beta which is embedded inside the alpha and k. So, we will use, instead of eliminating the arbitrary constant, we will use it to find out the expression for the beta. So, by looking at these equations we observe that on the left hand side and right hand side we have the arbitrary constants b and d. So, we can eliminate this b and d by dividing one equation by the other equation. So, by doing so we get, I am dividing the equation 2 by equation 1, we get k into tan k w by 2 equals alpha. This can be called as the characteristic equation to define or to obtain the value of the propagation constant beta. So, this equation is a transcendental equation. Where the constants, the required constant beta is inside the constant k, k0 square n 1 square minus beta square and alpha beta square minus k0 square and 2 square. So, it is not easy to solve this equation directly, but by programming either MATLAB or any numerical software we can obtain the values of beta. Before we go further, let us interpret this equation and how we can solve this graphically. Graphical solution of this equation can be obtained by looking at the left hand side and right hand side and the geometrical figures that they represent. So, the expression k tan k w by 2, let us say, is equals to y, and if we represent the independent variable by x, let us say this is x, and I will multiply the equation with w by 2 on both sides to get. So, we can say this is x tan x, this is of the form x tan x. We know the form of tan function, and x multiplied by tan x also would look somewhat similar. This is a form of the tan functions, or I should use a different variable, fine, even though I have used x for the other variable. Similarly, the right hand side of the equation, if we look at the definitions of alpha and k, can be written in terms of k again. So, w by 2 alpha can be written in terms of k as follows: beta square minus k0 square n2 square and if I add k square and alpha square, I get k0 square n1 square minus beta square plus beta square minus k0 square n2 square. So, the plus beta and minus beta can cancel and say that k0 square n1 square minus k0 square n2 square, or k0 square into n1 square minus n2 square. So, I can say, and multiplying by w by 2 on both sides, square of it, I can say, and representing this by some constant v square, I can say this is v square minus k square, where the constant v is defined in terms of k0 square into w by 2. Now, square can be removed, w by 2 into square root of n1 square minus n2 square. So, this is called the V parameter of the waveguide. With a slight modification, we can say this represents the V parameter containing the waveguide width, the refractive index, contrast, and through k0, which is equivalent to 2 pi by lambda, will represent the operating frequency. So, the constant alpha, if we are representing x k w by 2 as x, we can say this is equal to x square v square minus x square. So, we can say that this, if we say the first curve is y1, the second curve is y2, then these are curves y1s. This represents a circle of radius v. The right hand side of the characteristic equation represents a circle of radius v, and depending on the value of v, the point of intersection of these two curves represents the solution. That is how you can obtain the solution to this equation graphically. You draw the graph of left hand side and right hand side with normalized parameters like x, and then find the point of intersection, and from the value of the solution, the x, we can find out what is the value of beta. So, from this expression we have said that k w by 2 as x. So, once we got the value of x, we can find out the value of beta. That is how we can obtain the value of the beta. So, we observe that the radius of this circle is depending on the parameter v. So, v is the parameter which will define how many points of intersection we have. If the radius is bigger, this will intersect the left hand side curve at more points, and we can say there are more solutions. If it intersects only one curve representing the left side, you can say that there is only one solution and we have the single mode waveguide. So, we can design a single mode waveguide by choosing the parameters of the waveguide, like the waveguide width, the operating wavelength, and the refractive index contrast. As I mentioned earlier, we can solve this equation directly using a MATLAB, and you can find out what are the various solutions that we can get. Now, let us discuss a little bit about the design curves for a slab waveguide. We said that the design parameter V is given by k0 into width into square root of n1 square minus n2 square. I will replace the width parameter. Earlier we had w by 2 in the equations. Later on, when we generalize the theory to asymmetric slab waveguides, we see that there is a more general solution and w is the parameter. Or before going for that, I will go back and say that we can also think of symmetric modes. See, we have called these are asymmetric modes and these are symmetric modes. So, we have solved for a symmetric mode all the characteristic equation. So, we can also do the exercise for antisymmetric or odd modes by choosing sin kx instead of cos kx. We may end up in having cot theta instead of tan theta. So, the design curves are generally drawn as a beta as a function of width, how the propagation constant varies with the design the waveguide parameters. So, we can form a table of values of V versus propagation constant and then plot them as a 2-dimensional plot, V on one axis and the beta on the other axis. At this point, the propagation constant can also be normalized by saying that from the above theory we have found that beta should lie between should be less than k0 n1 for k to be positive and should be more than k0 n2 for alpha to be negative. So, k is positive if you choose this and alpha is also positive if you choose this. So, this range of values of beta has to be chosen for the what can be called as guided modes. Guided modes are the ones which have got a oscillatory nature in the guiding region and exponentially decaying in the cladding region. So, these are the ones which are used to guide the light inside the waveguide, and we can say that if we choose the value of beta like this, the mode is confined only to the waveguide region. So, this beta is normalized with respect to the refractive indexes as follows. Beta has got the dimensions in the free space, beta has got the dimensions of 2 pi by lambda into refractive index. So, if we solve for a particular beta and divide by 2 pi by lambda, so it has got the dimension of a refractive index. But as we see from this expression that beta lies between k0 and n1, and we can expect this eta this n to be lying between k0 n2 and k0 n1. So, and we can call it as an effective refractive index of the waveguide. So, this effective refractive index of the waveguide lies between the refractive indices of the substrate and the guiding region, and a normalized propagation constant can be defined as follows: as a B, which is beta by k0 square minus n2 square divided by n1 square minus n2 square. Later we will explore the logic, how the logic behind the definition. So, if we choose the beta like this, we can say that n effective is lying between n2 and this is n1, and so the beta will lie between 0 and 1, and the plots look like this. For the fundamental mode, the for whatever be the value of the V parameter, there is always a solution. So, we can say the fundamental mode always exists and starts at origin, and as we increase the waveguide width or the refractive index contrast or the frequency, you can say that it saturates towards some particular value. It looks like this. For the next mode, we can see from the characteristic equation, you can see from the characteristic equation there are multiple modes, and the second one appears after pi by 2. So, if we say that the odd modes are in between, we can say the cutoff of the modes to be pi, and it starts at this point. So, this is the typical nature of the curves representing the propagation constant with operating wavelength and the waveguide width. So, we will take up the discussion about the waveguides further when we go to the next exercise on the asymmetric slab waveguides.